Hello, everyone, and welcome back. My name is Mr. Koval, and in this video, I'm going to continue to talk about how to understand your equilibrium constant K and how to use that understanding to identify how to solve a particular equilibrium problem. So in my last video, I talked about what to do when K is small and you're starting with lots of reactant. But in this video, I'm going to talk about, well, what if K is large and you're starting with lots of product? So let's go over this example. And so again, before I get into this example, again, the rule of thumb is that if your reaction is going to be shifting in the direction of, I should say, um, away from the direction of the favored side, right? So if your reactants are favored and you're shifting away from the reactants, then that's an indication that X is going to be small, or the amount of change or the amount of product or whatever amount of the substance that you're shifting to is going to be small. You can ignore that in your ICE table and you can make the calculation smaller. Hopefully that was not too convoluted of an explanation, but hopefully my explanation of this example will help clarify what I was trying to say. So let's get into this. So in this example, I have very little reactant, in this case, zero reactant. So I'm starting out with zero reactant and I'm starting out with a certain amount of products. And so the other thing to pay attention to is your K value. In this case, the K value or the KEQ value for this reaction is very, very large, which means that if we understand what our equilibrium constant means, it means that we have a certain number of products over a certain number or amount of reactants. And if our KEQ is very, very large, that means that our products are heavily favored. So we have a lot of products and very few reactants at equilibrium. So for this particular reaction, the large KEQ is indicating that the equilibrium favors products. So at equilibrium, this reaction is going to have a lot more products compared to reactants. So we have a very, very, very tiny amount of reactants at equilibrium. Okay, so that's what you need to understand about a very large K value. And so here we're starting with a reaction that has K value that favors products. And on top of that, we are starting out with zero amount of reactants. So because we have zero reactants, we know that it's got to shift in this direction. It's got to shift towards reactants. But keep in mind, based on our K value here, the reactant side is not favored. So we're shifting towards the side that is not favored. And in that situation, we know that there's only going to be a tiny amount of reactant formed because it's not favored. It favors the products overwhelmingly. So in that case, we can go ahead and do an ICE table. We don't have to do stoichiometry, right? We don't have to do a stoichiometry table or an ICF table or anything like that. We can just jump in and do an ICE table, and then we can do our X is small approximation. We can neglect X, simplify the calculation, and solve for our change. And so let's get into this. So because I know it's going to shift this way, I can do the change part of my ICE table. So I know that it's going to shift this way. So I'm going to lose a 3x amount of this. So I'm losing on this side 3x amount. And I'm going to lose just an X amount here. So I'm losing an X amount there because, again, I got to pay attention to the coefficients and the stoichiometry. So if I have 3 here, I have to have a 3 here. If I have a 1 here, I have to have a 1 there. So here I have 1, so I'm going to gain on this side. I'm forming reactants. So I'm going to add an X amount there. I'm going to add a 2X amount there. Now, one thing I want to say before moving on is that students will have, you might have a tendency or an inclination to want to reverse the reaction because, hey, it's shifting this way. So technically, you might think, well, then this is the reactance and this is the product. So you might be tempted to switch the reaction and do your ice table. Don't do it that way, please. Whatever the reaction is, keep it that way. You don't have to switch the reaction. You just keep the reaction it's this way and just do the shift this way, right? So whichever way you're shifting, just do your, oops, sorry. Sorry about that. So whichever way you determine the shift is going, just do your plus and minuses for your x according to the shift. Don't flip your equation. Just do your equation the way it is, and just pay attention to which way you are shifting, and then do the signs of your changes accordingly. Okay, so if you start flipping things around, it gets complicated. You might forget to do something or take in consideration a certain thing that changed because you flipped the equation, and so just don't bother with that. Just follow along with what you're doing here and follow the steps like you normally do. All right, so now that I got that public service announcement out of the way, let's continue with this problem. So I figured out the change. I know it's shifting this way. I know I'm going to lose a 3x amount on this side. I'm going to lose an x amount on this side. I'm going to gain an x amount on this side, and I'm going to gain a 2x amount for a on this side. So now I've got the changes. So now I'm going to add them. And on this side, I'm going to have an equilibrium amount of 2x. I'm going to have an equilibrium amount of x for my b. And then here it's going to be 1.0 minus 3x for the equilibrium amount. And then here it's going to be 2.0 minus x for d. So now I have everything in terms of x. And now I have the equilibrium concentrations in terms of x. So now I can apply this to my K expression. So KEQ for this equation is going to be equal to the concentration of C raised to the power of 3 multiplied by the concentration of D raised to the power of 1. And that's all going to be over the concentration of A raised to the power of 2 multiplied by the concentration of B raised to the power of 1. And so here's my K expression. So notice that the K expression fits this equation, products over reactants. Remember, products are always on this side. Anything on this side of the equation, on the right side of the equation, that's your products. Anything on this side is reactants. So products over reactants. And so we can then plug in our equilibrium expressions with X. So C is going to be on top. So that's going to be 1.0 minus 3x cubed multiplied by D, which is 2 minus 0, or I said 2.0 minus x. And then we have 2x here. So this is going to be 2x squared multiplied by b, which is x. And so there's my equilibrium expression in terms of x. I can set that equal to my KEQ. So that's going to be equal to 1.0 times 10 to the 16 power. Okay, so now I can neglect x. I can do the x is small approximation. Why? Let's go back. So I know that I have a large KEQ here, which means that my products are very heavily favored. So it's going to shift away from the favored side. So it's only going to shift a little tiny bit. So that means that I can assume for the time being that this is going to be so small that subtracting it from these is really going to have no effect. So I can go ahead and ignore the changes here. And again, it doesn't matter if it's on top or bottom, as long as I can assume here under these circumstances that x is going to be so small that subtracting it or adding it to the original amount is really going to have no effect on the original amount. So I can just go with the original amount. Notice here I'm not subtracting x or adding x to anything, so I can't get rid of these x's. So I'm going to keep these x's, and then I'm going to solve for x. So then I have here what it simplifies down to is going to be equal to 1.0 cubed multiplied by 2.0 over, and then I'm going to have 2x squared. I'm going to simplify that. So I'm going to have that as 4x squared multiplied by x. That's going to be equal, this is 1.0 cubed is just 1. So that's going to be 1.0. And then that's going to be multiplied by 2. So we could just make that 2 because 1.0 cubed is 1. 1 times 2 is 2. So that's going to end up being just 2, 0. And then this is 4x. Oops, that should be squared. Sorry for got the square. So 2x squared is 4x squared. Okay. So then this is multiplied by x. So what I end up with is 4x cubed. And that's going to be equal to 1.0 times 10 to the 16 power. So now what I can do is I can use my algebra. I'm going to multiply both sides by 4x cubed. So then I end up with 4x cubed on this side. So I'm going to end up with 2.0 is equal to 1.0 times 10 to the 16. Oops, that's a 6. That should be a 10. Multiplied by 4x cubed. And then I can multiply the 4 by this. So then 2.0 is equal to 4.0 times 10 to the 16 times x cubed. And then I can just divide by 4.0 times 10 to the 16. This is going to be 2 divided by 4.0 times 10 to the 16. So this cancels out. I got this. So it's going to be then 2.0 divided by 4.0 times 10 to the 16 power is equal to x cubed. And so all I have to do is do the cube root of both sides. So I do the cube root of that. I do the cube root of that. And then this becomes x. And then I finally get x is equal to, what did I get? Give me a moment. 3.7. So that's going to be 3.6 or 7. 7. 3.7 times 10 to the negative 6. 3 times 10 to the negative 6. Let me write that better. So that is my x. And notice that x is here, right? So my change in x is really small, 3.7 times 10 to the negative 6, which is what I was expecting because it's shifting in the direction that is not favored. So I would expect a tiny amount to change. And notice that it's really small. So it seems like a good assumption, but let's check. We have to do our 5% rule. So what we do is we take the change, x, and again, you would do this for both of your concentrations here that you start, your initial concentration. So you're comparing the change with the initial concentration you started with to see how much of a difference it is. and we're going to calculate and see what the percentage is and see if it's less than 5%. If it's less than 5%, then that means that our assumption here that we can neglect x was valid. So let's see. So if we take this, right? So let's see here for a second. So here, let's take 3x. So that's our change. So this 3x here, we're subtracting it from 1. We're going to see if that's going to make much of a difference. So our 3x, so that would be, the change would be 3 times 3.7 times 10 to the negative 6. That's our change. And we're going to divide that by the original concentration, 1.0. 1.0 molar, right? So 1.0, and then we're going to multiply that by 100, and then we get our percentage. And what the percentage is, let me double check, 0.001%. So that's our percent. So that is well below 5%. So our assumption here, our assumption to neglect x because it's going to be so small is valid. And so we can go ahead and use our x value. So now we can use x, we can plug that back into our expressions here, and we can get the equilibrium concentrations of A, B, C, and D. So I hope this is helpful. And again, the rule of thumb that you want to follow is if your reaction is shifting in the direction of the unfavored side, then it's a good chance you can just do your ICE table, ignore x, and get a simplified calculation to find what the change is and go from there. Remember that if you're neglecting x or assuming x is small, you always have to do a 5% rule to double check to make sure it's valid. But so in some cases, it's clear that it's valid. Now, what happens if you're shifting towards the side that is favored rather than the side that is not favored? We said that the rule of thumb is if you're shifting towards the side that is not favored, then you know that x is going to be very small. You're only going to get a tiny amount formed on that side. So you can go ahead and do your equilibrium ICE table and assume x is small and move on and do your calculations. But if your reaction is shifting towards the side that is favored, then your x is small approximation will not work. And you're going to have to do a stoichiometry table first, or an ICF table, or whatever your teacher calls it. And then after doing your stoichiometry, then you can do your ICE table. I will cover that in another video. But for this video, I am finished. I hope this was helpful. Please, by all means, if it was helpful, please like the video, share it with your friends, hit that like button. Also, subscribe to my channel. Make sure you hit that click that all button so you can be notified by all the videos that I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.